Shri Guru Namaha Hari Om Sahana Bhavatu Sahana Bhunatu Sahaviryan Karavavahai Tejasvinamanitam Ma Vidvishavahai Om Shanti 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 Hari Om Namah Shri Adhirajaya Vivekananda Sudare Sachit Sukha Swarupaya Swami Tapaharini Om Shanti 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 Hari Om. We have already introduced you before your coming, just to save the time. Now it's your time.
Have the presentation.
Yes. Darshini is here.
Right. So lovely to be here. I met Swamiji a few days back, and that is when I got to interacting with some of the residents of two of the members of the ashram who are staying here. So the two traditions being those of, well, Vedanta and that of physics, right? So I'm Dr. Mrittunjoy Guha Majumdar. I'm currently a postdoc at IISc, as must have been mentioned. My area has been quantum physics. And some of you, or many of you, may have heard of the ways in which there are some interesting dimensions of physics that were found in the early 20th century. That was very different from physics as we knew it till then. Right? Physics as we see around us, right? Physics where there is a certain reality irrespective of how and when and who sees it, right? So for instance, if I were to talk about this speaker here, right, which is on this side, it has a certain dimension, it has a certain color, and regardless of I see it, you see it, anyone sees it, right? How I see it, right? It remains to be so, right? But there was a certain shift in the way in which physics was oriented in the beginning of the 20th century. Right? And that is what I will be expanding on. And when that shift happened, there were certain pioneers, right, who were supposedly influenced or were kind of very impressed with some of the ideas which were put forward by Vedantin Seers with Vedantin treatises. And we will see why the commonality or the bridge, if there is any, is present, but with a word of caution, right? Whether that is really true or not is the question we're trying to address here, right? So the question that I've asked here, which is a very provocative statement, right? Were ancient Vedantin Seers early quantum physicists, right? The Seers who gave us the Vedantin thoughts, right? The ideas, essentially, were they kind of going into the very fabric of reality, as we say it, in the physicalist manner, in the physics dimension of sorts, right? Or were they doing something more than that, right? So that is the key question we are trying to address here. So next slide, please. Right. So firstly, starting with this, let me ask you all, what do you think this is? It's a painting, okay. Anybody else? Is this man-made or is this natural? Okay. And how did they make it? What do you think was the physical system? What did they do here?
Microscope level of atomic.
Okay, that's one answer. Okay. Anybody else? Actually, let me give you a hint. Something similar to this. Sorry. Good. Right. So he got it. Yes. So this is not exactly oil. This is soap film. Actually, it's a specialized experiment. But the same thing you see on the ground when oil is spilled. Right. When you see oil spills, right, there is something called iridescence of light. Right. So oil slicks have iridescence of light. This is another form of that, a more specialized form of that. And it'll be of interest to you that back in the 17th century itself, Robert Hooke kind of tried to see something similar and study it in the feather of a peacock, right? And tried to see why that that color comes out, right? And it was very interesting. What he did was he put the peacock feather in water. It lost its inside. It was brought back, it kind of regained it, right? So there were some studies based on that. The reason I put this here is because one of the primary things as I went forward in my journey of physics or science as a child, as a youth as well, were certain stark kind of phenomena and things around me, which really struck me as interesting, fascinating even, right? And the reason I'm highlighting this is because this is exactly the way in which both scientists, the a certain color, let's say, right? What is happening there, right? And similarly, when we are talking about ourselves, right? Emotions, circumstances, events, right? Life, realities of life, right? These are things which are you're naturally curious about, right? Why is it happening in this way, right? So this is what I want you to kind of begin with as I start this kind of discussion, is that there is basically an exploration of truth at a very personalized level, right? That is the fundamental crux and kernel of science as well as spirituality, right, in a certain way. And that is why I will just highlight this point. I mean, it will come forward as well, that spirituality in the Indic and Indian context was never contradictory to science, right? It was never contradictory to science. At a certain level, it was probably complementary. Here, right? So the first one is I've written it as that which devours all, right? That which eats up everything or like consumes everything. Basically, that's a representation not quite of a black hole, but supposedly of a black hole. So many of you may have come across this recent image of a black hole, which was 19, right? And the Event Horizon Telescope kind of got that. And so this is one extremity of natural phenomena as we see it. Then we have something here where it says something very counterintuitive again. When twins no longer have the same age, right? When twins no longer have the same age, right? How can that be, right? Well, I mean, they're not exactly the same age anyway. Some minutes or seconds, some moments of difference. But here I'm talking about a significant difference between the two, right? And this is again another extremity of nature, right? There is a thing which is in relativity. Some of you may have come across relativity, right? Where they talk about the twin paradox, right? So if I take one twin, right, and put him on a space shuttle and send him off somewhere, right, and they go a fairly significant distance, right, and they turn back and come back to the world, the age of the two twins will not be the same, will be slightly different. There'll be a slight time kind of, difference between that, right? So this is something which is again very counterintuitive, right? This one I'll be addressing at greater length, right, which is to do with what is known as a Schrodinger's cat. I was told by Darshan that you guys have been trying to discuss about quantum mechanics and so on. The idea being that, well, something that's not quite the right wording for it, but in the popular science world, it's said to be something that can be both dead and alive at the same time, right? Both dead and alive at the same time. How can that be, right? You can either be living or you can be dead, right? You can't be the two of both of them together. So again, very counterintuitive, very strange, but this is how the physics world, certain concepts and constructs of physics world are, right? And so now all of these things, right, there often is a certain dichotomy, a certain difference of what we see around us, right? And what at a greater length or looking at it in greater detail has to be the reality as such, right? So now the question is that what is reality, right? I mean, reality. I mean, well, this question is reality or is reality? Well, this question is reality real or is reality an illusion? These are things which because these are things which our intuition or our common experience how can this not attest to these? Right? Something how can this be the case? Right? Something must be off. I will take it even further now in the next few slides, and I will take it even further now in the next few slides. And so there were some fundamental shifts that happened. But I just want to give you a feeler of how, well, counterintuitive and strange the world of physics and the universe can be as of sorts. Right. Next slide, please. Right. So now, I was mentioning in the beginning that there were certain explorations of truth, right? And there were certain expressions of truth on two levels, right? The two levels being because we are the individual, without is outside, right? Exterior and within, right? So now you know these three definitive kind of stages of human evolution. The first one is that of 300,000 BC, actually 300,000 years ago, right? And that is when apparently the first evidence of fire building was found, right? I mean, the extent or what is existing today. As per that, in Israel, there is a certain, let me just be correct in this, Kesem cave, right, which is in Israel. And there is an archaeological site where they have found a hearth, right, a place where you build fire and cook, basically, right? So this is one of the first evidences of hearth, regularized way in which man used fire, essentially, right? So earlier also they used to have it. They used to replenish it with fuel or other things, wood and all. This was when they started having. Then they have, sorry. Yeah. So then there is 2100 BCE roughly, where there is a certain place in Israel, again, very active place of sorts, right, which is Ohalo 2, right, where you have around, well, 11,000 years before regularized agriculture came to other parts of the world, you can find certain kind of small scale agriculture happening, right? And then in 4000 BC, you obviously have the wheel, right? Now in all of this, right, when I talk about explorations without, right, what is actually happening? Right? We're trying to extend the boundaries of what we are or what we're capable of, right? And it is coming from a certain exploration of the things around us or how we can manipulate and utilize the elements that we have accessible to us, right? So for instance, it's fire, it's, crops, and then the wheel, right? Next slide, please. Right, and concurrently, or well, not concurrently, because this is not exactly 300,000 years back, but around, 70,000 BCE, this is something that has been found in Nagamiland, Botswana, right? This is a very interesting kind of rock art, which where they found the first elements of rituals, right? Rituals as it was back in Africa. And they found that there was a certain cult or ritualistic tradition around the python, the snake, right? So there was certain python worshipping people essentially that were found, right? So this was again a way to relate to some elements that they felt was important by reflecting within, right? So there were certain things, rituals. What is rituals, right? You relate to some elements which you formulate as a way to understand yourself in a certain manner of speaking, right? Then there is a Pestelaz, which is in France, right? Here you see this is from a burial site in Pestelaz, where there are some engravings. You can see there are some marks on that, bone-like structure, right? And those are one of the first evidences of, these engravings, deliberate engravings, to kind of make them pass into what they thought was the afterlife, right? So where does afterlife come in? Afterlife comes in because of mortality, right? So the idea of mortality, that somebody is living, somebody is thriving, one fine day, and the next day they are not, right? So there needs to be a certain continuity of sorts, and that is where the whole idea came forth. Although there is a spiritual dimension to it, which I'm not touching upon right now, right? And then there is a Stonehenge, right, which is obviously you all may have looked at, and that also had a certain element to it. There was a burial element, ritualistic element to it as well, right? So these were all elements which kind of came out of explorations within potentially, and also the Indic side I'll be explaining in a bit. So there were two kinds of exploration that were happening, right? And the only idea was that about what is existence, right? What is reality? Who are we, right? This fundamental idea of truth, exploration of truth, and the inner and the outer levels, right? So next slide, please. Right, and in India is never behind, and India wasn't behind at all. So Bhimbetka, right, is a famous kind of rock art, site, and there is evidence of prehistoric religion there. There were certain kind of markings which were found. Bhimbetka, by the way, the meaning is the resting place of Bhim, right? So from Pandavas, from Mahabharata, essentially, right? So where Bhim rested, basically. So Bhimbetka. And then something which is of interest to you, and I'm going to touch upon this point more soon, is the idea of the development of geometric theories for Vedic rituals, right? Very interesting, very interesting. So I want to be a little factual here. So in fact, the Sulba Sutras, right, and the Shatpat Brahman, these are two texts, two treatises, which are extremely, important in this regard. They talk about the dimensions of places of worship and rituals, for instance, right? And they are representative or metaphorical in certain ways, right? So for instance, the Mahabedhi is that the place where you have the rituals essentially, right? there is a certain kind of geometric aspect to that, right? So in fact, it is supposed to be an isosceles trapezoid, right? Which has bases 24 and 30 and a width of 36 units, right? Very precise, no ambiguity on that front, right? And there were certain fire altars which were there with around 21 around the earth altar, 78 around the space altar, and 261 around the sky altar, right? So obviously there was a metaphysical, a metaphorical level of understanding why those numbers were there, but there was a very clear-cut geometric dimension to it. And the reason is actually very fundamental, right? And physics, modern physics and maths is kind of giving us that, right? The whole idea that at the end of the day, physics and the world, the universe, is actually geometric. This is a very fascinating idea, right? The world is composed of a number of what we call mathematical groups, right? I won't go into too much detail on that, right? Mathematical groups are what? These are higher dimensional representations or groups of constructs, right? Like geometric constructs of sorts, right? So at a very fundamental level, the universe is that, right? So the idea is that back in the day when they were trying to do this development of the geometric idea, it was to represent a bigger reality in a smaller scale, right? In a representation of that essentially. And it's very fascinating that this was happening around 8th to 6th century BCE. So again, I go back to the point, right? The inner and the outer, right? There was no dichotomy. There was no division. It was a very accessible, personalized kind of way of exploring this dimension of sorts, right? Please go ahead. Right. Now, there's a very famous sutra, the one that fascinates me the most in the Rig Veda, right? The Nasadya Sutta, right? And the reason I have put the Nasadya Sutta here is because it gives us the extent or the height of Indic thought back then, right? How profound was their formulation of the universe, right? And mainly, I would like you to kind of focus on the last 4 verses, right? Whence all creation had its origin, the creator, whether he fashioned it or whether he did not, the creator who surveys it all from the highest heaven, he knows, or maybe even he does not, right? Now, it's not that they didn't have an idea about what they're talking about, right? It's not that they just took up paper and one fine day they was just like, started writing something and then they thought that, well, we don't know what they're talking about, right? The reason they said this last line, right, is very important. This is the seed of agnosticism, as it is called, right? The fact that you have a certain element of accessing the truth, right, and not preaching to somebody, right? So it being something which is an exploratory way of understanding truth, right? Instead of a descriptive model of the truth, essentially, right? And so the idea is that even science, right? When I suppose I'm a very eminent, or somebody is a very eminent scientist here, right? And I say something, right? And there is a experiment or a thought, right? A theoretical construct by which you think that what I'm saying is not true, right? Or it's incorrect, right? I mean, it is absolutely, not true, right? You can, right, stand up and tell me you're wrong, right? Now, this is something which is very important, right? Truth is as it is, right? And my saying it or your saying it is something which is should not like make it pathar ka lakir, as we call it in Hindi, right? The idea is that you seek the truth, right? You explore for the truth, right? And there are elements of subjectivity and objectivity to it, right? So in this Nasadya Sutta, what they were trying to say, the Vedic seers at the height of their wisdom, essentially, was this accessibility of the truth, right? Instead of kind of preaching it in a certain manner of speaking, right? So it's a very refreshing thing to see that the Nasadya Sutta, which is in the Rig Veda, right, was present. Next slide, please. Right, and the idea of Ritam also in the Vedic civilization came to the fore, right? So what is Ritam? Ritam is the order of the universe, right? Or the way in which the principles that define the universe in a certain manner of speaking. And it is important because, again, this comes from observations, right? So you see that fire burns a certain way, the winds move a certain way, gravity happens a certain way, right? So there is definitely a certain order of sorts which exists in nature, right? So this whole idea of order and principle way of working, which is also true in science, right? We find formulas, equations, we try to understand theories, right? What is that? We're trying to understand the dynamics of nature, of various physical systems, and trying to make a theory of it, right? So Ritam in Vedic civilization, and there are certain resonances across in various different civilizations, right? So in Egyptian civilization, it's called Math, right? Greek paganism, Logos is more than this, but there is a certain school of thought, which is called the Stoic Greek paganism, Stoic school of thought, which talks about the same Ritam kind of idea. And Chinese civilization, obviously Taoism and Tao, right? They also spoke about this element of sorts, right? So there is a certain understanding and identification of this principle and order of nature, basically, which was very much present. Next slide, please. Right, and before I move forward into the Western kind of side of things, I'd briefly like to kind of highlight three people whom I really admire and appreciate their work of sorts, right? Kannad, I hope I'm correct now, yes. Right, and his work on atomism, right? The whole idea of Anu and Parmanu, right? The whole idea that everything can be subdivided into a very basic unit of sorts, right? And what one can do with it, how the entirety of nature and the universe comes from that, right? So that is something which he gave, and he was the founder of the Vaisheshika school of thought, Vaisheshika Sutras, basically, he gave, right? Then Aryabhatta, right? Obviously, extremely kind of, prominent, eminent person, right? And his works in mathematics as well as in application of, if I'm not incorrect, planar trigonometry and spherical geometry, right, for various kinds of celestial systems is still kind of accepted and appreciated, right? And Bhaskaracharya, again, calculus, right? They say that Newton and Leibniz gave us differential calculus and so on, but there is a school of tradition which says that, in fact, Bhaskaracharya was also very much out there in terms of calculus. Yeah. Next slide, please. Right, and now briefly like to kind of highlight this verse, right? I wouldn't go into too many verses, don't worry. This verse I feel is the center of Hinduism, right? I feel this is the central thesis of the dharmic ideation of the universe, right? And the reason is because what it is doing, it is, okay, so which Upanishad, anybody, if people are into Upanishads, do you have an idea which Upanishad this could be from? It's a very, very eminent, famous shloka. Nanta pragyam na vahi pragyam, na bhatya pragyam. This is the shortest Upanishad, or one of the, I'm pretty sure it's the shortest. The Mandukya Upanishad, right? So the verse 7, right? So this is basically what it is saying is, right? So the English bit is here, right? It's talking about the ultimate reality of the universe, right? So it says, as not inwardly conscious, not outwardly conscious. And I want to, well, take that word conscious with a pinch of salt. I mean, let's discuss that further. But for now, as not inwardly conscious, not outwardly conscious, as not filled with a knowing content, not conscious, not unconscious, unseen, non-predictable. Sorry, that should be predictable. Or it could be actually predictable as well. Ungraspable, bereft of quality, unthinkable, indeterminate. As a substance of the certitude of an unitive self, as a calmer of the unmanifested, tranquil, numinous, non-dual, is the fourth limb considered to be. He is the self that is to be recognized. Now, in this, I want you to grasp a few things, right? One is that, paradoxically, ironically, the ungraspable, right? Grasp the ungraspable, right? The reason here is because what they're saying is that there is no way to describe it, right? There is no construct, no way to describe it beyond a point in its entirety, essentially, number one. Bereft of quality, right? Very important. This you will find in many Vedic and Upanishadic thought, bereft of quality, indeterminate, again, which again goes back to the ungraspable, right? Unseen, right? And non-dual, right? This word is very important. Non-dual. What does it mean? Dual means which are two, right? This and that, right? Non-dual is which is not that, right? I mean, which is just one. And it's, oh, sorry, there's a very important thing. It's not one, right? It's not two, right? Because this is it's not easy to understand this, I guess, in a way. But when you say one, right, there is always the other for the one, right? When I say not two, right, there is no other for the one for that, right? It is negating all duality, essentially, right? So this is very important, non-dual, right? So I'll come to the quantum mechanical side of things as well, and then I'll kind of try to connect certain aspects of that. Yeah. Anyway, so this is very important. I personally feel it's the central thesis of sorts. Yeah. Next slide, please. Right. And these are the Mahavakyas, but I just want you to kind of understand or focus on the first two, maybe. Yeah. The first two, basically, Tattvamasi, right? That thou art, and Aham Brahmasmi, right? Now, in the philosophical and cultural context, we talk about it as us as human beings, as philosophical constructs. But I want you to think of it as a unit. You're a unit of nature, right? and there is a greater reality of nature, right? So Brahman for the moment, right? You can think of it as a fundamental greater reality of the universe, right? And this line at the end, which I've written, right? This oneness of reality, right? The oneness of reality, any element you take, right? If you, like a formula, if you were to apply that thou art and I am Brahman, right? Has to invariably be connected to the greater reality, right? In essence, in effect, right? So oneness of reality, very important, right? Beyond and emanating from the physicalist multiplicity. What do I mean by that? These are words, which is that multiplicity means the number of things we see around us, right? Now, this reality, the oneness of reality is coming from beyond the reality itself, right? This is very important. It's coming from, because you remember the last slide, I said ungraspable, indeterminate, all those aspects, right? So it's clearly not something, because I can see the things around me, right? So that reality has to be beyond this. Simple, right? Logic is simple. If I'm able to see these things, if I'm able to describe these things, that reality is beyond this. But now we are also saying that the Mahavakya, that I and everything I see around it, in essence, is also that, right? So what does that mean? That means there is a reality which is one, but that oneness is coming from beyond this realm, this domain of reality itself, right? So it's emanating from a more fundamental reality, right? So this line I would like you to remember, and this Mahavakyas you may have seen. These are very famous Upanishadic Mahavakyas, the four big ones, right? Yeah, okay, next slide, please. Okay, and I just highlighted these three verses because I want you to keep this in mind as we go into the scientific side of things, right? That is one of my favorite treatises in the Vedic, Vedantic and Dharmic side, the Avadhuta Gita. Very tough to read and grasp. It's by Sri Dattatreya, right? Who's said to be the guru of Parashuram, right? Sri Parashuram. And here he's talking about this verse, right? There is no action. There is no present, future, or past. Very dramatic, right? There is no action, there is no present, future, or past, right? Which has been performed or enjoyed by me. This I know without any doubt, right? So he's not only saying that I'm conjecturing this and maybe thinking about this, because, well, he was a realized, this comes from a very kind of certain different, stature of sorts. But he's talking about this, very interesting, right? So some of you may have read recently, there is an article which you can go back and read. It says that there is no time. There's no time, right? Time is an illusion, right? This is not from Avadhuta, it's not from Dattatreya. This is from physics and mathematicians of today's age, right? So there is no time, right? Time is a construct, it is emergent, right? There is something more fundamental from which it comes, right? So very interesting. I mean, I don't want to bridge it yet, but I just want you to keep it in mind, right? Yoga Vashishta, right? This is Sri Ram's guru, right? Vashishta, so Maharishi Vashishta. He wrote, again, a very famous treatise. Water in the mirage does not come into being and go out of existence, right? Even so, this world does not come out of the absolute, nor does it go anywhere, right? He's going even further. The creation of the world has no cause and therefore it has no beginning. It does not exist. How can it reach destruction, right? So he's saying that what I think Shankaracharya and various others were mentioning, that the whole multiplicity of reality is an illusion, right? It's an illusion. There is actually no such multiplicity, basically, right? And he's saying it in a very dramatic and drastic fashion, right? The last one, Maitriya Upanishad. There are two ways of knowing reality. One is through sound and other is through silence, right? This is very important. And this is because there's a story, right? Buddha, when he was asked if there is a God, right? One morning, one of his followers came and he said, is there a God, right? He was, I think, silent and he may have nodded, right? And then somebody in the evening came and said, is there no God? He then did the same thing, right? And everyone was like, what is wrong, right? It has to be one or the other. It can't be both, right? Now, there is a certain element which is very important, and that is the last element here. Through sound as well as through silence, both you can access it, right? Which means that any binary, this or that, any duality, right? It transcends that, right? If it were to be, entrapped by this, right, then it couldn't have done that, right? So anyway, we'll come to that again in the quantum context as well. Okay, next slide. Okay, yeah, and this is basically, so it's all about paradoxes, right? So I mean, the Indic thought, Dharmic thought is all about paradoxes, and this is increasingly what in the modern context in physics you will see as well, right? So some of you may have heard about wave-particle duality, right? Object is both a wave and a particle at the same time, right? Then there is various complementarity relations, right? The position, momentum complementarity, energy, time complementarity, and so on, right? So there are various ways in which there are paradoxes, things which are binaries or which are not, well, how can a particle and a wave be the same thing, right? Think about it at a very deep level, right? What is exactly happening, right? So this paradoxical nature of reality is something that the Vedantins and various others did deliberate on and did speak about. There are treatises. I gave you evidences of treatises, right? And we'll come to it from a quantum and a physical kind of dimension as well. Next slide, please. Right. So all of this was happening in India and around, essentially, right? But on a different front, basically on the physical front, on the Western Occidental thought front, there was a whole line of things that were happening, right? So Aristotle came, he gave us Aristotelian physics, right? Archimedes, he gave us buoyancy and various other ideas on that front. Ptolemy was very important on the celestial and astronomical aspects. Copernicus, heliocentricity of the solar system. Galileo, very interesting. He gave us these ideas on gravity, right? Gravity, he had the famous experiment. He went to the Leaning Tower of Pisa, dropped balls from there, right? And he saw that regardless of the size and the weight of the ball, they fall at the same time, right? They reach the bottom at the same time, right? And various experiments with pendulums, inclined planes, and so on. Newton, behemoth, right? All are giants, but he's a behemoth, right? The first unification of, well, a lot of things. Actually, the first grand unification of physics was kind of done by Newton because he elaborated on calculus, he elaborated on mechanics. He even had theory of sound, for that matter. He looked at gravity, of course, right? So he did a lot of different things, and he defined the course of physics for the next 300, 400 years, right? Till Einstein came about. Newtonian physics, broadly speaking, with certain other elements of all what others have done, was the primary strand of physics, right? Then Bernoulli came, Bernoulli's theory again in calculus as well, I think. And then Maxwell, obviously, the second grand unification of sorts, where electricity and magnetism was unified, right? So electricity and magnetism and light are the elements of the same physical system, right? The same physical entity, essentially. So Maxwell was the next behemoth. And Stokes. Stokes is somebody who worked on fluid dynamics, right? Fluid dynamics of sorts. Now, okay, so now I want you to kind of look at, so what is happening here, right? So this is a system which is a very interesting system. Well, it's a play thing of sorts. It's called a Zorb, right? A Zorb. So you can see, if I ask you, what are the different physics? What is the physics going on here? So obviously there's classical mechanics, friction, gravity, and so on, right? Then there are four-stroke engines, which are classical thermodynamics. Now, all of that is more or less classical physics, right? Which Newton also looked at, various others looked at. Now, what if I stretch the application of physics to extremities, right? So if I say it is either at an extremely small layer of reality, like a very small scale, or it is traveling at an extremely high speed, right? What is the physics then, right? And I say this because in the 20th century, this is exactly what the people were doing, right? So there were two different extremities which were explored, right? So relativity was one and quantum mechanics was the other. So let's go forward and try to expand on that. This quote is very interesting because by the end of the 19th century, there was a certain smugness, a certain arrogance in the Western world, right? The scientists thought they had discovered everything, right? There was nothing left to be discovered or explained. Everything was done, right? Done and dusted. So in fact, in the last line, right, you can see this. An eminent physicist remarked that the future truths of physical science are to be looked for in the 6th place of decimals, right? So if I just find another place of the decimal, that's all I have to do, right? All the theory, constructs, conjectures, everything is done. So this, why I'm saying this is important, is because this is the context in which Einstein came into being, right? He not came into being, but he put forward his theories, right? So in 1894, this is a theory, this is a quote, right? So there was a lot of arrogance on the Western front, right? And then within a decade, well, an explosion happened, right? What was the explosion? The explosion was the year of miracles. It's called Annus Mirabilis, right? 1905. So Albert Einstein, put forward 4 different papers. These are the original papers. I've given this screenshots of the original papers. You can find this online. You'll probably be able to find some copies. And they were primarily on these 4 effects, right? Some of you may have read all of them, some of them. Photoelectric effect, right? Photoelectric effect, special relativity, Brownian motion. This is the least known of the 4, I presume. Not many have heard of this. And mass energy equivalence, right? Mass and energy are the same thing. They're equivalent, right? E is equal to mc squared, right? The famous equation of Einstein, right? So 1905, he gives this theory. 1894, he's talking about having discovered everything, right? So I just want you to understand that there are these phases of smugness that comes into being, right? And one should be very careful about them. Anyway, next slide, please. Right. What was happening just before that? I'm just giving a little bit of background before I go into full-on quantum mechanics, right? So light, when it comes to light, right, in the 17th and 18th century, okay, if I were to ask you all, right, some of you have read about light and so on. What is light? What is light? Is it a, let me not even define anything. What is light? Any of you? It's a form of energy. Okay. But like, could you elaborate a little more? Something, anything. I mean, no pressure there. Just any aspect of it. Yeah, true. Very technically correct. But I'm asking more in terms of the form of the radiation of the energy, right? So the idea was that it's a wave. It is a wavy nature. There is a wavy nature, right? So Hooke, Huygens, Euler, 17th, 18th century, they're all about this aspect. They did a lot of definitive experiments and they found this, right? And Thomas Young, very famous. Some of you may have gone through the double slit interference experiment. Okay, yeah. So this is known, right? Double slit experiment. And then there is cathode rays. Cathode rays was by J.J. Thomson Moore, actually. I had the privilege of being able to see that equipment back in Cambridge. It's still there. And very, very kind of path-breaking, because back then there were very few apparatuses and equipments available. He kind of made a mark there. And then there is also the idea of black body radiation, right? So now, sorry, yeah, some question. Okay. So now the law of thermal radiation, right? Why is this important? Why is light and thermal radiation important? Because there is a certain way in which the physics that was there till then was not able to explain some experiments, right? So for instance, a black body, right, as the name suggests, is an entity which is entirely black, right? And what it has is that its emissivity, right, which is the tendency to emit light or to accept light, is the maximum. Right? It's the best, right? So that's the standard bearer, that's the reference point, right? Now, there are some ways in which the theory till then, right, could not explain the fact, this thing that the Kirchhoff's law of thermal radiation gives, right? And there was this thing called ultraviolet catastrophe, right? The energy had to shoot up in a certain way, in a certain experiment. It was not explicable as to what you were seeing and what the theory was giving you, right? So there was a certain difference between the two, right? So next slide, please. And so Ludwig Boltzmann, right? He was one of the first people who said that instead of thinking of it as a continuity, as a wave, right? It could be discrete. It could be specific. There's a certain distinct, discrete levels of energy, right? And thereafter, Max Planck, one of the big ones, 1900, right? He says that the energy of the oscillators in a black body is quantized. Now, I'll just highlight. I'm not sure how many of you understand all of it. So the idea is that in the black body, there are some oscillators, right? Oscillators. And these oscillators have, they have discrete energy levels, right? And there's a specific way they release energy, right? And the energy of these oscillators is quantized. That's what he said, right? And he was trying to explain the difference of the experimental finding and the theory, right? He was trying to give another theory to explain the experiment, right? The only difference between Einstein and him was that he was talking about the oscillators. Einstein said that light itself is discretized, right? Light itself comes in packets of energy, right? This is not a continuous wave, packets of energy, right? So, so that is very important, right? Now, before I go forward, I just wanted to show you this picture. This is, maybe some of you are aware of it. It's called the Solvay Conference, right? 1927. It's the coming together of some of the greatest minds of that age. I don't think there has been such a meeting ever again. So you can see everybody from Debye to Dirac to Einstein, Lorentz, Curie, Bragg, Heisenberg, Pauli, Schrödinger, Born, Bohr, Brillouin, Ehrenfurst, all of them, right? The big ones. Everybody who was of any significance back then was all here in this picture, basically, right? So just to kind of show you an interesting coming together of minds. Yeah, let's go forward. Right, and so okay, so not only were the problem of this discretization present, right? There was also a fundamental another aspect which Albert Einstein was also struggling with, right? In fact, at the end of his days, actually. I'll tell you what he was struggling with. He was struggling with entanglement, rather. But he speaks about this quote, right? Let me just read this quote to you. It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either, right? We are faced with a new kind of difficulty. we have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do. Right? So he's talking about there are two contradictory pictures of reality, right? What to use, what not to use, when to use, right? What is it actually? What is reality, right? So he was really struggling with this idea, right? So you can see this from this quote, right? Now, from 1900, well, around hundreds, Max Planck's time, for the next 2 or 3 decades, these 5 people give us very important ideas, right? So the Bohr model, all of you have seen the atomic model, right? Atomic model. So the Bohr model, he gave some ideas on the orbiting of the electrons, right? In certain quantized levels, right? Complementarity and correspondence principle, I won't go too much into it. Then there was also the idea that there is a uncertainty involved. Sorry, yeah. There is a certain uncertainty involved with the properties of an entity, right? Now, if you go up there again, right, he is talking about uncertainty in what is the reality itself. He is talking more about in terms of the properties of the particle, right? So that level also there is an uncertainty involved as such, right? And there is a matrix formulation, and then, well, de Broglie gave us the wave-particle duality. Then there is Dirac, who gave us quantized gravity and Dirac equation, and Schrodinger. I'll be expanding on the Schrodinger equation in a bit, right? Next slide, please. Yeah. Now, so this world that they had kind of, okay, it was like a Pandora's box, right? So they had started with Max Planck's idea of what is the, the way in which radiation happens. And Einstein had gone ahead and done the photoelectric effect, discussed about the photoelectric effect. But there was something more dramatic and more drastic in terms of the properties, right, which was found. So from the energy aspect itself, they found that the energy has to come in packets, right? It can't be a continuous. So you can think of this policeman, right? He can slide up and down the pole, right? I mean, if he requires. And so there is no discreteness to it, right? There are infinite number of points he can go up and down to, right? Whereas for the quantized picture, if you think of it as a ladder, right, there are specific rungs that you can go up in. Right? So this is first property that came forward from the energy aspect itself, is that the quantization of reality, or the properties of reality or entities, basically, right? So classical particles and quantum particles, right? So the first fundamental shift. Next slide, please. Right. And then the slightly more paradoxical elements, right? Or the slightly more difficult elements to understand. So the first one is superposition, right? So if you see around you, right? If I talk about this wall here next to you, right? I wouldn't say that it's a superposition of the black and the blue and the green and the red and the gray, right? I wouldn't say gray plus black plus blue plus green. It doesn't make any sense, right? It's gray, right? So the whole idea of superposition of particles, or properties of particles rather, is something which comes from actually wave aspect of things, right? You can have superposition of waves, for instance, but also from a fundamental shift in the way we perceive of the properties and the way they develop and evolve as well, right? So that is where the whole idea of the Schrodinger's cat comes in, right? I'll not expand too much on what the Schrodinger's cat is going to point. It is very simple. It is basically a room, right? You have a cat, right? You have a radiation source, right? And with a certain probability, the radiation source can get released or not, right? If it gets released, the cat dies. If it does not get released, the cat lives. Right? I go out of the room, I leave the system as it is, right? From outside, if I ask you, is the cat alive or dead? What will you say? You will say it is either dead or alive with some probability. But here they're talking about actually neither of them is correct, because, well, it is correct to a certain margin of error, a certain kind of probabilistic element, right? The most correct aspect of it would be that the thing released and he died, plus the thing did not release and he lived. Right, technically, right? So there is a certain element of that, and that's where this superposition, the cat being alive and the cat being dead, right, with its normalization constants, is being shown here, right? So it's an interesting idea of sorts, which again came from the quantum aspect of things, right? And lastly, decoherence. I'll not explain too much on that. So decoherence is basically when the quantum system, right, correlates with the classical world around us. Right? So the quantum system has some properties. The classical world is what we see around us, right? So there are certain ways in which the quantum system relates with the world around us, right? And the way it does is that it starts to develop correlations between its properties and the world's properties, right? In the process, it tends to lose its quantum properties. It tends to become classical in certain ways, right? So that is a very important aspect. But the most important aspect actually and which I want you to focus on, is the idea of reality, right? The idea of reality. If I'm saying that the superposition principle is valid, right? And if I'm saying that there are some other aspects which are, as I was discussing about, are valid, what is reality, right? If I were to talk about, let's say, the color of that, I was doing the color example, what is the color actually, right? If I ask you that, what will you say, right? Is it that my observation, right, is defining the reality, right? Because if I were to look at it as gray, is that making it gray, or has it always been gray, or what is it, right? So this element of what is reality, right? What is objectivity, objective reality, is a very important concept, right? A fundamental concept. The other is that of non-locality, right? And I will go a little bit into non-locality now. What it means is that, what is locality? What is local? Let me ask you, what is local? What is local? Something which is around you, right? Something spatially close to you. Non-locality would mean something not spatially close to you, right? Now, if I would say that the core properties of two particles, right, even if they are very far apart, right, they are still connected, right? That is non-local, right? Now, that is a fundamental idea which is not quite true in the, it is true. I mean, for instance, if you call a wall in a wall, right, the atoms next to each other are correlated. They are stuck together, right? So it has to have correlations. But if I were to say that I have a particle here and I have a particle in the next galaxy, right, and I'm saying they are correlated, is that possible? In the classical domain, can you think of something like that? It's difficult, right? Because if you have a property, just think of the way in which you can do it, right? So you start with properties which are correlated locally, right? I take one particle and go off to the next galaxy, right? That is the only idea, right? But in that process, there can be a lot of losses, ways in which it evolves, changes, etc. What I'm saying is, regardless of how far you take it off, obviously there are quantum decoherence effects and so on, it will still maintain its correlations, right? It's a very important concept here, right? Now, so these two things, reality and non-locality, was around what the debate about what is quantum mechanics carried on for Einstein, Bohr, and various other people. I'll just come to it in a short bit. Next slide, please. Okay, now this is an interesting, so this is a clip from a movie. It's called Casper the Friendly Ghost. I'm not sure if many of you have seen it. It's about a ghost, basically, in a certain house, old house, right? And there is a girl who comes with her father to live in that house, right? And the ghost's father, back in the day, was a famous inventor, like a scientist, right? So they make this very interesting chair and this whole device. I'll just, let me just show you the clip. Can you please play the clip? You go back, I think. It's a clip, actually. Yeah. Yeah, so this girl has just come to live in that house with her father, and she comes across this small ghost, right? And I'll just change the premise a little bit, right? On the chair, I put a sensor, right? A sensor, what does it do? It determines whether the operation has been done well or not, right? So if it is done fine, if it is done satisfactory, it will be done very good, right? So it will have some mode, right? Some setting, which will tell us that, right? Based on what the operation has been like, it will go in one of three different tracks. I'm changing the premise a little bit. One of three different tracks, right? Or three or more different tracks. Now, think of all of the laws of quantum mechanics in terms of that, right? Very simple. Now, the thing is, why did I give two different premises? What have I done? Only two main things, time evolution, right? And this sensor-based kind of picture, right? Because in quantum mechanics, there are two fundamental elements only, right? Mainly, right? Evolution, which is continuous, right? The track was continuous, the person was moving continuously. and something which is slightly discontinuous, which is abrupt, which is based on what the measurement, think of that as a gate operation, right? What was happening, the brushing and everything, right? Based on how that measurement happens, what happens in that measurement, right? The further evolution is defined by that, right? Two elements, evolution, measurement, simple, right? Now let's go ahead with all these ideas, right? So these are the laws of quantum mechanics, right? So there is something which is called the psi bracket notation. Think of it as a representation of that chair, right? The chair or whatever the person is, right? It's a representation of the chair, right? The operator is that gate where the brushing and everything was happening. So some measurement was happening there, right? And it was defining the further evolution based on that, right? Now, the eigenvalues, right? Eigenvalues are what? These are the 2 or 3 different possible measurement results that could have happened, right? So the brushing could have been good, bad, satisfactory, right? So these are the eigenvalues, right? And then the probability of the eigenvalue, right? If, let's say, I have a very balanced experiment, right? 33% of the time it could be good, bad, satisfactory, right? If I make the comb very good, right, then most probably it will be doing a good job, right? So in the same way, the probability, right? The probability is defined based on what kind of experiment, how you're doing it, and so on, right? State vector collapse, what does it mean? Basically, based on the measurement that you have done, right? If it is a good measurement, the track that it takes, right? That is a collapse. What happens is it takes up one of the measurement results and further moves along in that kind of an evolution, right? So that is the state vector collapse. Based on the measurement, the state it assumes and carries forward, right? So that is a state vector collapse. And Schrodinger's equation is basically, think of the track, right? And the time evolution. What is the fundamental equation or the theory which defines it? So it's just a mathematical theory. So you can see a d of dt. Those of you who are familiar with mathematics and calculus, I'm sure most of you are. That is how the time evolution is happening, right? The differential of that representation with respect to time. So just think of it as a time evolution operator there, right? In a certain form, right? You have to go into the mathematics of it further. But for now, just based on that particular analogy, I've tried to explain these postulates, right? Now there is so that is a hydrogen wave function, right? When you think about the atoms and the electrons, right? In the classical picture, you had circular things, right? Orbits. In this picture, it's fuzzy. There is no definite trajectory. There is only a cloud. Think of it a cloud, right? A fuzzy cloud. So you can see here, I've called it quantum fuzziness, right? So this electron can be somewhere in that fuzzy cloud, but I can only define a certain probability of finding it in a certain place, right? But there is no definite movement trajectory, right? That is a fundamental difference, right? So in that classical case, there is a certain trajectory. In the quantum case, there isn't, right? There is an idea of quantum tunneling also, which is very simple. So I just these two are things which you won't find in the classical world, but in the quantum world, right? In this picture, for instance, you can see there is a hill, right? A ball is coming up, going up the hill, going down, right? The ball can never go through the hill. Simple, right? If I make that hill very high, it will not even go up the hill. It will not go on the other side. But in the quantum domain, and there's a whole mathematical reason for that, it can actually tunnel through the hill. Right? It's a very counterintuitive idea because it is in terms of a wave, right? So the wave thing can spread, it spreads, right? So it can spread regardless of if there's an obstacle or not. So it's a little more complicated than that, but I just want to kind of give you a flavor of how the quantum world is very different from the classical world as such, and then give you a bit of an idea of the postulates of quantum mechanics, right? Next slide, please. Okay, I'll just quickly, this is like a game, right? Okay, I mean, it's a little complicated, but it's like a game. So there are 4 schools of quantum mechanics or interpretations of quantum mechanics, right? So just like a game, if you start from the beginning, right? Ask the question, does quantum theory describe an objective reality which is independent of the observer or not, right? So if I see something, right, and you see something, regardless of who sees, is there an objective reality or not, right? So if it is a yes, right, then it is a realist theory, right? If it is a no, it is an anti-realist theory. Right? So let's go down further, right? So if it is a yes, realist theory, then we say that wave function, that way of representing, does that constitute a reality or it's just a mathematical idea, right? That is the next question, right? Again, yes, no, right? If it is yes, there is something real about that wave function representation. Is it on its own or with something else, right? That's the next question, right? So then you go forward and somebody will say that, yes, it is its own reality. It is a reality by itself. Others, there is this thing called pilot waves. It is something which guides the reality, right? With other things, it's a reality, not by itself, right? So there are two schools of thought that comes from there, two famous scientists, David Bohm, right? David Bohm talks about implicate order, right? The order of nature. And he says that wave functions are like pilot waves, waves that carry particles along, right? And there is Hugh Everett who talks about wave functions being their own reality, right? On the other front, when I said no, right, wave functions do not constitute their own reality, then there's Einstein's theory, Einstein's idea, right, which says that it's just a probabilistic understanding. It's a mathematical construct, more or less, right? It's something deeper is present, right? And it's just giving an idea about that deeper reality, right? So in fact, Einstein, for the longest time, he was fighting over this idea that something hidden variable, he called it, right? There is something hidden in the universe. We don't have access to it. But if we had access to it, it would be completely deterministic, like classical, right? But because we don't have access to it, it is probabilistic. It becomes probability based, right? So that was his idea. It's called the hidden variable theories, right? So he gives that. On the other front, completely, if quantum theory is not independent of the observer, that is what Niels Bohr gave us, right? Saying that the wave function describes the quantum world because it accords with the observation. So there's a certain way in which observation and the wave function are intricately linked in a certain way, right? Niels Bohr, Einstein, Bohm, and Everett. These are the four major theories of quantum mechanics, right? So just give you a feel of it. So it's like a game, right? You just go through it and you get to the four theories of quantum mechanics. Yeah, go ahead. Okay, I wouldn't focus too much on this because I want to go to the next bit as well. Let me just check the time once. Okay, 7:16. Okay. Let me just quickly go through this as quickly as possible. So quantum entanglement is related to the non-locality principle, right? The idea that connections of the properties remain even if they are spatially separated. They're non-local, right? Let's go ahead and see how that happens. So Einstein, right? So Einstein, for the longest time, with these two people, Podolsky and Rosen, right? EPR and Schrodinger, talked about the spooky nature of reality, right? The spookiness in reality, basically saying that how can something be connected in this fashion, right? When it is spatially separated in this manner in which it does, right? And so this idea of entanglement was actually put forward by Schrodinger. This is the word, the German word, Versprangen, right? And basically what this entanglement is what? Entanglement is saying that if you have, let's say, okay, very simply, let me just try to put it. So if there are 2 or 3 balls, right, and I bring them together, they still remain the addition of these 3 balls, 3 or 4 balls, right? But what if I were to say that the balls merge, right? Balls merge or they become they take a different form together, right? They melt into each other, let's say, right? Then I cannot talk about the addition of these balls. There is something more than that that has happened, right? The forms are not exactly the addition of these balls, right? Similarly, if there is a global state of a system, right, which cannot be written as a product of the individual subsystems, right, that is entanglement. Simple, right? It is correlated in a certain way such that the separability of these states no longer remains. We cannot speak about it as separable subsystems as such anymore, right? So this is the feature that they were talking about, and Einstein, well, in his typical fashion, was not very amused with it, although he seems amused here. Okay, next slide, please. Right, I wouldn't want to focus too much on this. This is one of the famous ideas. So I'll give the simpler example of this. The simpler example is that right, a position momentum uncertainty. So if I were to have 2 balls that come out from a certain place, right, a certain center point, right, and I have the distance between the 2, right, and I have the wave, the momentum and position uncertainty as well that I have in me, right? If I have just 2 of these, like, so there are 4 variables: position of the first, momentum of the first, position of the second, momentum of the second. I can determine what the position and momentum of the other can be as well, right? Because of the difference and the uncertainty principle. I don't want to go into too much detail on that, but there is a certain way in which paradoxically you can find things which you should not be able to find, right? Properties or values of properties as such, right? And that is what Einstein was not very amused with. Let's Yeah, so he said that, this is a newspaper article from back then. And he says that there is a whole description of physical reality that can be provided eventually, right? That is not there yet, but we will someday find it, basically, right? So it was only in 1964 that John Bell, right? He was a British physicist. He finally completely dismantled Einstein's ideas. This hidden variable formalism was destroyed by him by some experiments, right? So he showed that there are two schools of thought, Einstein school of thought and Copenhagen school of thought, right? Which is to do with, there is no hidden variable. Nature itself is probabilistic, right? There is nothing else you have to add into that, right? So John Bell showed that that is indeed the case. Einstein's theory is not correct, right? Or this idea formulation is not correct. And there are three elements which are very important, even in day-to-day life, right? Reality, locality, free will, right? What is reality? What is locality? What is local? And if you have a free will, when you're doing an experiment, you should have your free will of what you want to do, right? It should not be defined by what the other person is doing, right? So these three ideas were very important. And when Bell was doing his experiment, I won't go into too much into that. Let's go to the next slide. So this is one of the inequalities which comes into the picture, CHSH. Those of you who are interested, I can share the relevant details about it. And that kind of proves that the classical and the quantum, right? So you see that if Einstein's theory was correct, the red line should have been followed. In practice, it was the blue line that was seen in an experiment, right? It was a detector-based experiment in optics. And this is what was found, and that was what was supposed to be found. So Einstein's theory is not correct, basically. Next. Okay, and so there were various other people who gave us, so this is a way of representing, so you can see the interconnectedness of various things, right? They're all entangled. There are different dots, right? These are all particles. They're connected with each other in a very intricate manner in a certain fashion, right? So this is a particular state, a particular quantum state, which is entangled. I just wanted to show you that, right? And this is another kind of such state. Next slide. So yeah, I mean, this was actually the experiment which was done. Which proved Einstein incorrect. It was Alan Aspect, French physicist, who did this test, right, of violation of the Bell inequalities, right? And since then, the local hidden variable theory are incorrect. That has been proven to be wrong. Okay, so entanglement in the lab, right? I just want to give you a big feel of it. This is entanglement in a lab. What is happening is there is a beam of light. It is hitting that crystal, right? And there are two light beams that are coming out from there. Right? This is called an SPDC process. Those of you who are interested, I'll give you the details. SPDC process. So what happens is the two light that comes out, right? They are entangled, right? In some property, they're entangled, usually in polarization, right? So this is what you see in the lab. You see two such rings, right? So what happens is you're doing multiple runs of this, right? Each time, these two things that are coming out are in diametrically opposite directions. So if I were to see these rings here, right? If I take one beam to be on that side, if I draw a diameter, right, the other beam has to be on the other side, right? So this is what you see in an experiment. This is an actual demonstration of entanglement in a lab with light, right? So I just wanted to show you that. Okay, I don't want to kind of go too much into this. These are some of the ways in this aspect. There are some distance measures and some mathematical constructs which can be helpful for defining what is entanglement and how to describe it. Yeah. Next slide, please. Okay, now one of the things in which I'll just be okay. Right. Okay. So one of the things in which entanglement is very important is that of some of these protocols, right? And it's very interesting. Some of you may have heard of Star Trek, teleportation, right? What if I were to say that teleportation is possible, right? Quantum mechanics makes it possible, right? With the caveat that it is not teleporting one entity to another place. It is rather taking the information in one entity, transferring that information through a channel, reconstructing it elsewhere, right? Absolutely same state, right? But not quite the original state, essentially, right? So this is a scheme of doing it, right? Those of you are interested again, with light, right? There are things called Bell state measurements you can do. And then you can recreate this state here on the left-hand bottom corner, right? On the top right-hand corner, you can see there, right? So there are some measurements you do and some transformations, mathematical transform, or rather experimental transformations. And that gives you the state on the other side, right? So there are various things you can do with it. Nowadays, quantum computing, you have heard many of you, IBM, Microsoft, they're all doing quantum computing, right? Cryptography, right? Super dense coding. These are all because of entanglement, more or less, right? So this is the central resource which gives you all these capabilities. Next slide, please. And so you can manipulate entanglement, you can broadcast entanglement, you can control and distribute entanglement, right? You can also make multiple states within one state with entanglement. So there are very complicated ways in which you can manipulate entanglement as such. Just to give you a feel, again, I'll forward this to those who are interested. There are many papers and works which you can look at. Next slide, please. Okay, because of dearth of time, Swamiji, how much time should I? I have a few slides, not many, so about 15 minutes. Yeah. Then I can probably show this animation. If you can click on the. So the way in which the wave particle duality comes into being will be shown in stark contrast here. So if it is a wave, it is a particle. Right, right, like a fringe pattern, as you call it. So a quantum object, it's a wave, but as soon as you measure it, it collapses to 1 point. So let's say 1 point, right? Again, you will observe it 1 point. But when you do multiple runs of this, it will recreate the fringe pattern, right? Very interesting. It is a particle, right? But it has a wave-like element in terms of the statistical average. So you can see the fringe-like thing has come, but it is only on the ensemble runs of it, right? Multiple runs of it. Now, if I were to put an observer in one of the slits in front, it becomes a particle right there, right? It becomes a particle right there. As soon as you bring an observer, it becomes a particle. It collapses. I was talking about the collapse of the wave function, and it becomes only one, right? One or the other. So it stops being the wave-like character, completely goes here, right? But the third one was what is interesting. It is a particle, but the bigger run, see here it is random because I've introduced an observer there, right? When I did not have an observer, I was having one particle hitting, but multiple runs of it gave me back the wave-like characteristic, right? So that gives the idea of wave-particle duality. There is a wave-like tendency. It just so happens that each of them in an ensemble is a particle actually, when you're observing it, technically speaking. Yeah, next slide, please. So it's a very paradoxical idea, very strange idea. Okay, Schrodinger's equation, very briefly. Next slide, please. So the way in which, so in mechanics, you have the laws of mechanics, right? So V is equal to U plus AT, right? And for distant displacement and so on, right? So there are some equations, right? Governing equations. In quantum mechanics, it's almost like a black box, right? You have a certain equation called the Schrodinger's equation, right? Which depends on the potential, basically, and the time evolution. I showed you in that slide, right? And you just pass it through it, right? And you get a certain evolution of the particle, right? The key point here is that this Schrodinger's equation gives us only the evolution, not the measurement aspect, right? Measurement is a discontinuity, as I showed you in that clip, right? So anyway, please go ahead. So that is the equation, those of you are interested. So this is actually, it's nothing but an energy conservation equation, right? So the left-hand side first term is a kinetic energy, right? Second term, potential energy, right? Last term, complete total energy, right? So that's all it says, right? That delta square is actually h cross square by 2n delta square is p square by 2n, basically, right? And v and that e, right? So this is energy conservation. This is the governing central equation for a quantum particle's evolution, right? So there are some properties, linearity. Linearity is that if you add two particles, they add up in a linear fashion, right? They don't have nonlinear terms. Unitarity, I don't want to go into too much into that. And also there is a probability-based aspect of it, which is important as well, right? And if you just, that is also actually a video. So the complex plot of a wave function, it will go around, it will turn and move forward basically. It's okay, it's okay. Basically that form kind of rotates and moves forward. The wave functions elements, right? They move forward in a certain fashion, right? That's all I want to show you. Okay, next slide, please. Okay, now coming back, right? So I've shared two elements, two aspects. One is the spiritual aspect and one is the quantum aspect. Now, firstly, before we discuss about what others have said, did you find resonances between the two? I'll be more specific, right? Interconnectedness, right? Non-locality, right? What is reality, right? Reality, whether it is even there or not, and it is actually dependent on your observation of it, right? Then about the way in which superposition happens, right? Nonlinearity on that front as well. So there are some elements which, if you look back on the treatises that I discussed at the very beginning, right? Elements in that, properties in that, which have strange resonances with what we have learned in quantum mechanics now, right? Or at least seen some flavor of it, right? But there's a caveat, and I'll come to it, right? Please go ahead, next slide. Okay, so there are some famous scientists, these are all famous scientists, right? And they all were there in the very beginning of quantum mechanics, at that early phase, right? And let's see what they're saying, right? They're speaking about, so Max Planck talked about consciousness, right? He was talking about consciousness. And he, well, made very dramatic statements. He said consciousness is fundamental, matter is derivative of consciousness, right? Everything we talk about, everything postulates consciousness, right? Now, the first question that should come to your mind, right? Unless you are, just blindly listening or accepting whatever he's saying, what is consciousness, right? That is the first question that should come to your mind, right? Is consciousness what we say is biological consciousness? Is it some field of theory of physics? Let's say, right, a quantum field, a classical field, what is it, right? That is the first question. And I want to just keep that seed of thought in your mind. I don't want to address it right now, but just keep that seed of thought in mind, right? Then there is Eugene Wigner, right? There are two kinds of reality. Again, he talks about existence of consciousness and reality of existence of everything else, right? Again, consciousness, right? Now, then there is Eddington, very famous. No one can deny mind is first. Most things in our experience are next. I want just briefly to connect this to the idea of observers, right? You remember in that simulation that I was running, as soon as I added an observer at any point in the experiment, it changed the entire experiment, right? Earlier, when I did multiple runs, there was a wave-like nature to it. As soon as I added the observer, it became a random kind of distribution. Very strange, right? There has to be one reality, right? If a quantum particle is particle, then randomness is fine. But when I didn't have an observer, it was showing a wave-like nature, right? So reality itself seems to be dependent on observer being there or not, right? Very strange. Consciousness, your observation, right? Okay. Consciousness is never experienced in the plural, only in the singular. Okay? Very interesting idea. Schrodinger said this. Just mind you, Schrodinger, the Schrodinger equation person, right? And so question of what role consciousness plays is very important. Okay? Again, back to the observer effect, right? Next slide, please. Now, the two of the biggest persons, like Schrodinger and Bohr, right? So Schrodinger was moved by the Upanishads. This is a documented fact, right? And this is something you can read about at length, right? He discussed with everyone he met about how to incorporate Vedantic thought. In fact, his tombstone, this is, I have to kind of, I think this is very much true. Multiple sources have seen this. So all being is one and only being, and that it continues to be when someone dies. This tells you that he did not cease to be, right? Very interesting. That moved, that influenced by it was he, right? Niels Bohr said, I go to the Upanishads to ask questions. Right? Niels Bohr, the famous physicist. So did Vedanta form a certain influence on the formulation of quantum mechanics, right? Natural question, right? But one must be careful in that, right? And I'm coming to why that should be so. Next slide, please. Right. So before I come to that bit, Schrodinger also, even though he was so influenced, he did say, take it with a pinch of salt, right? Take it with a pinch of salt. So he said, I do believe that this is precisely the point where our present way of thinking does need to be amended. Perhaps a bit of blood transfusion from the Eastern thought, right? That will not be easy. We must be beware of blunders. Blood transfusion always needs great precaution to prevent clotting. We do not wish to lose the logical precision that our scientific thought has reached, and that is unparalleled anywhere at any epoch, right? So he's saying there are resonances, appreciate it, understand it, but with a pinch of salt, right? Because the way we have come to these ideas on scientific front has nothing to do with the philosophical aspect beyond a point. There's a sequence. I showed you the exact trajectory in which things happen, experiments happen, and what was going on, right? But there are resonances. Now let's go forward. Okay, and now this is where a simple argument, and an important argument at that. The consciousness or the fundamental reality, right, in Vedanta is said to be beyond physicalism, right? That is the first idea, right? And I'll come to another thing called quantum vacuum. Many of you may have heard of quantum vacuum. There is a void, right? Everything comes out of the void as soon as you put some energy into it, right? That's the quantum void. Even that is not Brahman. And I'll tell you why. Because in Advaita Vedanta, when we talk about the substratum of this universe, right, which is even finer than energy, right? We call it Brahma Chaitanya, right? Brahma Chaitanya, right? That is beyond physicalism. That is beyond qualification. That is beyond description even, right? That is what it is spoken of. The very nature of the substratum is Satchidananda. Now that also can be what is Chit, what is Sat, what is Ananda. There's a philosophical, there is a physicalist, there's a spiritual understanding of that as well, right? Everything we see around us is due to the cosmic superposition of the unreal and the real by the agency of Maya. Now, many people, many popular scientists have mentioned that Maya could be something like, the energy, the pranic side, the energy aspect of it, and the Purusha or the Brahman is the wave function aspect of it, right? The wave function we're talking about, right? Now, even that has a certain caveat again, because wave function you can describe, right? There are certain characteristics of it. There are certain emergent and certain kind of existent aspects of it, right? So there is something more fundamental, right? Now, next slide, please. Right. So now, this is a very important thought, right? Saying that the Vedantin Seers who wrote and deliberated on the Upanishads knew quantum physics is not just incorrect, it is also underselling the Upanishads. And I'm being very blunt here. And the reason is very simple, right? The reason is that when we talk about space-time and causality, right? Space-time, cause-effect, right? You read any of the treatises, Upanishads, and so on, they talk about that being emergent from the fundamental layer. It's emergent. Space-time comes from that, right? In the Sankhyan philosophy, we talk about Purusha Prakriti, right? Purusha Prakriti, Moola Prakriti, right? Purusha has a discontinuous jump to Moola Prakriti gives rise to everything else, right? So physics and science, right? Because we are doing experiments are done in space-time with cause and effect, right? This is the emergent layer. There is something much more fundamental, right? With tools in the emergent layer, you cannot explore the fundamental. It's just inconsistent, logically speaking, right? You are at a certain layer, you're going to go below that. You don't have the tools for it. You just have the tools for the higher level up there, right? So it is not possible, right? So there's a fundamental bound to that, right? And that's a very subtle point which must be appreciated if you want to be consistent with the Upanishads, right? If you want to make all kinds of popular science ideas and popular fiction ideas, no one is stopping anyone from doing that, right? So the Upanishads highlight that space, time, and causality emerge from Brahman, right? Therefore, experiments in physics that rely on these three elements, space, time, and causality, would invariably never be able to explore or study Brahman. It may be able to see signs or derivative properties or resonances, maybe, right? But even there, you cannot be absolutely certain about it. That is a different dimension altogether, right? That is why the exploration of Brahman is always said to be intuitive, always, right? Vedic seers, Upanishadic thought, everywhere, intuitive, right? So we must be careful of connecting spirituality and science without qualification or thought, right? Because one of the biggest failures in science was the non-ability to detect ether. You may have all heard ether, akashic energy, akash, right? In the Western construct also, there was this idea of ether. Ether is this universal medium, which is everywhere in the universe, right? And it is the fifth element in Aristotle's thought, right? Earth, fire, water, sky. No, earth, fire, water, the wind, and akash, ether, right? So these were the four elements he mentioned. Others also till 20th century we're talking about ether, right? So I'll just give a few slides about how that was an absolutely bogus idea, right? And one should be very careful about that. Next slide, please. Because ether in the Western construct was taken in that way. That is the wrong point. That is what I'm trying to highlight here, right? So Galileo, right? He was one of the first people who said that everything in nature, right, has the principles of science or the principles of physics are same for everyone, right? Regardless of if you're moving, if you're stationary, everything. That's called the principle of relativity, right? The laws of physics, mechanics, there is no privileged observer, basically, right? Maxwell, right? He spoke about ether as well, by the way, right? He spoke about optical and electrical phenomena through ether, right? Which suggested that there may be something which can give us the idea of ether. And this is Newton's work, famous work. There is some mention of that. Next slide, please. Yeah, so ether, where art thou? Right? Plato, Plotinus, all of these people. I don't want to spend much time on this. This is a famous, I think, Roman thinker, Greek thinker, Roman thinker, and Plato obviously is very eminent. They both spoke about ether, but there was no evidence. Next slide, please. Right, just quickly, these are some experiments, right, which were done in the 19th and 18th and 19th century, or the 19th and 20th century, which was trying to see ether. In the first experiment, they were trying to see if light, when it moves through water, does it have any shift in its properties, right? That is what it is trying to do there, right? Here it is saying that if it goes through a crystal, does it change? Because ether is supposed to drag things along with it, right? So if it is dragging things along with it, the material itself should change, right? Does that affect the light as well? And so on, right? None of this found ether, right? Next experiment, and next slide. And finally, the Michelson-Morley experiment. Some of you may have seen it. It's basically a very simple experiment. Light goes through a beam splitter that splits the beam. If you play it, it goes through, hits two mirrors, comes back, right? Now, if I change the distance of these mirrors, right, that should change the pattern I see on this screen, right? Now, if I were to keep it the same distance, both the branches, and if I were to say that there is ether, the branch which is in the direction of ether should feel a drag, should feel some effect of the ether on the light, right? And that should be noticeable on the screen. That is not seen in experiment, right? That is not seen in experiment. This was the most definitive experiment that disproved ether, which went on from Aristotle's time to the 20th century, right? So one has to be extremely careful about spiritual, metaphorical ideas and principles to be transcribed directly into physics, right? It has to be tempered with the truth at the physicalist level as well, right? Next slide, please. Yeah, the final bit here, right? So quantum theory I was talking about, when you bring in relativity and quantum theory, right, there is something called as quantum field theory, right? Quantum field theory. And there is something called the quantum vacuum, right? What is it? As the name suggests, it's vacuum, right? But if you put energy into that vacuum, right, there are some excitations of that vacuum. Those excitations are the particles associated with that quantum vacuum, right? So it's almost like it seems to be empty, right? But with enough energy content, particles will pop out, right? And if you may have heard about particle, antiparticle, right? If particle and antiparticle collide, they extinguish. They go back into the quantum vacuum. The energy is released, right? Now, many people have been talking about the quantum vacuum, whether that's Brahman, right? Not true, right? The reason is very simple. The reason is that even though the quantum vacuum is vacuum, right? And this is one of the fundamental points where physics still has not found a resolution for this. There is a quantum vacuum for all the different fields. QED has a quantum vacuum. QED is quantum electrodynamics, right? Light, electricity and magnetism. QCD, which is quarks, protons, inside protons are quarks, right? QCD is strong force, one of the forces of physics. That has a vacuum, right? So each of these vacuum are actually not vacuum. They have some characteristic properties in them, right? So as soon as I give them energy, one specific kind of or few specific kind of particles only can come out of it, right? Which means that also cannot be Brahman, because Brahman is unqualified, without characteristics, without any aspects to it, right? So there is something more fundamental than that, right? Quantum vacuum still is one level above or few levels above. We haven't got there yet, right? LHC still is working at 125 GeV, right? The Large Hadron Collider, right? Nowhere close to even the next Higgs boson. The next Higgs boson is 700 roughly GeV, right? So even with 40 years of work, right? So many countries, right? So much of money going, they've only reached 125 GeV, roughly around that range, right? So we are very far away from getting to even the Planck scale, or even a fraction of the Planck scale, right? So the whole idea of unification and what is there beyond the unification scale is an elusive dream as it stands. And there is a reason for it, a simple reason, and I'll close with that. The reason is that energy, when it started off, the Big Bang happened, right, in the universe, there was a certain energy content, right? The Big Bang happened, energy got dispersed, right? Now, if you want to recreate that energy, because you have to recreate that energy, right? You have to get to that scale. You cannot, because fundamentally it has got dispersed, number one, right? Number two, it requires you to kind of, create, well, that is actually the only thing, that the energy constraint is that the entire energy is no longer accessible to you, right? Even the solar system put together, right? Very small scale of energy, right? So there are people like Weinberg who talks about the first 3 minutes of the universe, and the first 3 minutes, there's a famous book, right? We may not be able to reach there. That's a very humbling thought, right? That we may have theories of physics and science, but how much can we prove it empirically has caveats in it, right? And there's a very simple logical reason for understanding why that is the case, right? So again, I would like you to take 2 or 3 major things from here. One is absolutely the exploration of truth, right? Both the levels, right? See and appreciate the resonances between the two, right? But the places where there are claims, right? Claims which are oftentimes to kind of get some kudos or some, views or some thoughts from people, right? Has to be tempered with reality, right? Be consistent with both the sides. If they truly do coincide, only then accept it, right? So truth all the way. That's truth along triumphs, as we say, right? Satyameva Jayate, right? So I think I'd like to close with that. Thank you. Any questions?
Sir, is quantum tunneling related to wormhole?
So, okay, it's a very good question. So I'll just, how many of you are familiar with wormholes? Wormholes? Okay. Okay. So wormhole comes from the cosmological aspect, as you will know, right? So it's basically curvature of space and time. Just for those who are not familiar. So the black holes, right? You all have heard of black holes, right? So the black hole is when, so gravity is no longer a force in the way Newton said it, right? It's not a force. It's more a curvature in space and time. Space and time, think of it as a tarpaulin sheet, a sheet basically, right? And think of balls, right? Or objects put on the sheet. What will happen? It will curve, right? The ball will be there, it will curve around it, right? Similarly, gravity is curvature of space and time, right? Now, if something is very massive, a lot of mass involved, right? There is the tendency of it to go so deep, that depression to happen so much, right? That there is something known as a black hole that gets formed, right? It is almost like a, well, people in popular science say that it is a sink, like a sink, right? Everything goes into it, nothing can come out of it. It's not true, because Hawking radiation is something, there's a kind of radiation that comes out from a black hole, right? Well, we'll not go into that. Now, wormhole is supposed to be this conceptual idea that there are, let's say there are 2 black holes, right? Or actually technically one is called a white hole, right? 2 black holes, right? And there is a bridge between the 2, right? So there is something is kind of like a sink, and from the other side, it goes to a certain place, and again, there is another sink. So it's connected, 2 sinks connected, basically. Think of it like that, right? Now, quantum tunneling, right, is from the minuscule aspect, right? From the atomic, subatomic aspect. It is because of the wave-like tendency and the wave function dynamics of it. However, there is a recent theory, which is called the ER is equal to EPR theory. I don't know if you've heard of it. So it says that whenever 2 quantum particles, right, or quantum entities get entangled, right, there is an equivalent wormhole which gets created, right? Now, that also comes from string theory and ADS-CFT, right? ADS-CFT is a theory. Now, well, there is no kind of conclusive proof for that, right? Because at that level on the quantum side, as well as on the cosmological side, as you all know, till now we have only one photograph of a black hole. That too is with a lot of reconstruction and a lot of other things, right? 2017 to 19. 2017 they got the data. 2019 they released the image, right? N87 super black hole, basically, right? Supermassive black hole. So when we have only reached one image of a black hole, then experimentally proving whether there's a wormhole, and also one of the problem is how will you even experiment on a black hole, right? As soon as you go into a black hole, right, well, that's it, right? Your entire content will get scrambled, as it is called, randomized, right? So yeah.
But still, we can do the experiments standing in the event horizon.
No, because no, but the thing is, there is light also does not escape from it, right? Light also does not escape from it. So what will be your experiment? Let me just ask you this: what kind of experiment will you do there, standing on the event horizon?
Whatever, maybe take no photograph.
But photograph is inherently dependent on light.
But still, there is a jet of light that goes.
No, that's a common misconception. So when you talk about Hawking radiation, right, and what is emitted, that is randomized light, randomized information, right? So when you take in something, right, it gets scrambled, it gets destroyed, it gets randomized, right? That is emitted at a certain frequency after a certain period of time, right? So it is not the same thing that went in, or even the things that are there, right? It's a fairly randomized kind of emission of sorts, right? So what can you even recreate with something which is that randomized, right? Because, and if something is a sink, right, you will not be able to see anything in there, right? See, think of it as like this. Think of it as a abyss, right? A complete dark abyss, right? What do you even see from there, right? You can't see the other side, right? If hypothetically it's there, right? Even the one which is just inside, right? That bit also you cannot, what can you speak about it, right? If you look at the photograph that has been taken, you can only see, what can you see? You can only see a disc of black, right? With some swirling light around it, right? That's all you have to be able to see, right? So yeah, I mean, there are only limited things you can do, right? And also, if you were to be able to do it, the quantum aspect of it, how can you cover that, right? Because, okay, I'm not sure whether you've read about ADS-CFT. ADS-CFT, no, okay. So, okay, just a little bit of tidbit. ADS-CFT is a theory which was given by Maldacena, there's a physicist. He said that there is a gravity, right? Think of it as a bowl, right? A bowl. The rim of the bowl, right? If I take a quantum theory on the rim of the bowl, and I take a gravitational theory in the bulk of the bowl, there is an equivalence between what is happening on the rim at the quantum level and what is happening in the bulk in the gravitation level, right? Now, this is an equivalence which is still a conjecture. It's not conjecture, it's a theoretical construct of sorts, right? So people talk about how you can make space-time out of entanglement. It's a very interesting idea, right? A Japanese physicist, I think, has mentioned about it. But these are still at the theoretical level, right? Till date, there is no such kind of, evidence to that, right? Beyond a point, it's a theoretical construct. So yeah, I mean, you can have experiments on both sides, whether it bridges, whether it does not, and even the experiments, I'm not sure whether you're able to do it. So yeah, there's some constraints. I mean, that is the unfortunate thing. Even, I mean, Hawking didn't get a Nobel Prize, right? I mean, one of the reasons was because the picture came after him, and there is no way, certain things can be seen. So in Nobel Prize is only got when you prove what you have said. Right? Higgs gave the theory in 1964. He got it in 2010, after 11, 12, 13, something there, right? 40, 50 years after, right? Because there was no evidence till then. So, yeah. Any other question? Yeah.
So, in that mice, we studied that attitude. So there was like 1 by root 2x.
Yes.
Why was it 1 by root 2?
Because normalization. So if you so the probability of both the states, right, has to be half and half, and that's the idea we are going with. It could be otherwise also, but the probability, I think, all the postulates.
Before that, actually, there are actually 4 possibilities.
Yeah.
Like both the cat alive, both the cat dead.
No, there's only one cat.
Okay.
One cat, yeah. And only one cat, a room and radioactive source. Yeah. So yeah.
1 by root 2.
Yeah. So it's actually modulus squared of the coefficient, right? So 1 by root 2, modulus squared, half. Right? So half of it being alive, half of it being dead.
And regarding that, in one more video, we saw that like spin quantum number, based on the spin quantum number, it's like an electron is having both spins.
Yes.
So to understand quantum mechanics, they explain like if there are 2 electrons in one cell, okay, or any one cell, So if one is having
entanglement, you know?
Yeah.
Oh, no, I mean, so there are 4 EPR states, as it is called. EPR is Einstein, Podolsky, Rosen, right? Okay, so what is entanglement? Entanglement is basically that they are uniquely connected to each other, right? So now I can have 4 combinations, right? Yeah, because I have this idea of phase also. So if I say up, up, plus down, down, right? Up, up is first state, up, second state, up. So they're unique. If I see the first one is up, the other one will be up. Other one down, other one down. The other is up, down, down, up, plus, right? And there's also the minuses in between. This is because of phase, basically, right? So there are 4 states. So in principle, even with up, up and down, down, you can have an entangled state, right? It does not have to be up, down, right? So yeah.
So are we talking about in the electron level, or is it like matter and antimatter?
No, no, it's only electron level at that point. But I mean, that's a good question. Yeah. Okay, so if you talk about particle and antiparticle, this is theory that at the event horizon, right, at the black hole level.
Like this entanglement, are we talking about like between 2 electrons?
At the moment for this bit, it's only for a certain particles basically, 2 particles basically.
Okay, it's not about
not particle, antiparticle. But I mean, you can think about that. I mean, I invite you to think about that. There are some bits even in the event horizon of the black hole bit, which is very interesting. With that, right?
So yeah. All this quantum mechanics is working on just between 2 particles.
No, it need not. It need not. I mean, it can be for, so when we talk about quantum field theory, right, when it is relativity is also involved, then you have antiparticles in it, right? Because in fact, all the properties that you have, if you time reverse or reverse it in certain ways, that kind of gives the antiparticle aspect of it, basically, right? So you can talk about that. There are various chirality and various other aspects. Okay.
Those who have
yes. Okay. Or even, I mean, I can give the email if they have detailed questions or something. At some point, I can. Right. Okay. Sure.
Because that moment when it comes to ಯಾರಿಗೆ ಆಸಕ್ತಿ ಇದೆ ಅವರು ಯಾರಿಗೆ ಅರ್ಥ ಆಗಿದೆ ಅಥವಾ ಅರ್ಥ ಆಗಿಲ್ಲ ಸಾಕು ಅಂತ ಅನಿಸಿದೆ ಮುಂದಿನ
पुंडरीकाक्षः सर्वयज्ञेश्वरो हरि तस्मिन् सृष्टे जगत्कृष्टं प्रेणिते प्रेणितं जगत् हरि ओम तत्सत् श्रीरामकृष्णार्पणमस्तु।